Okay, so now I want to go through a couple of examples to show you how we actually analyze whether a mechanism that is given to you is reasonable or not. And as a reminder, we have three criteria to analyze this, which is the one shown here in red, right? And that is that the sum of the elementary steps in the reaction has to add up to the total reaction. We're going to just use uni and bimolecular steps in Chem 12. It's not going to be anything higher than that in molecularity. And then lastly, we have to derive a theoretical rate law, and that theoretical rate law has to match with the experimental rate law that we're given. Okay, so let's take a look at our first situation here. And this is a type of mechanism that you will often see for a chemical reaction, which is a reaction where the first step in the mechanism is the slowest step, or is the rate determining step. So the reaction is given to us as H2 plus 2 ICl forming I2 plus 2 HCl. We were told that the experimental rate law, which again has been determined for us, is rate equals K observed times H2 times ICl, both of them to the first order. And we were then given a proposed mechanism, which is shown there, step 1 and step 2. And we were told that the first step is the slow step, or the rate limiting step. Okay. And we're then asked if the mechanism is reasonable or not for this reaction. Well, we're going to go through our three different categories of confirmation tests. The first one is just adding the reaction, making sure that the sum of the reaction is the same as the total reaction. We're just going to add these two reactions. If there's any species we can cancel, we'll cancel them out. It looks to me like the HI here can be canceled. And then we have H2 plus 2 ICl forming I2 plus 2 HCl. And of course, that's exactly what the overall reaction is, this on the top here. So we satisfy our first criterion. An important thing to point out is that HI is an intermediate because it's produced in one step, it's consumed in the other step. Okay, now the next requirement is that each of the steps has to be either uni or bimolecular. So we have to determine the molecularity. And remember that the molecularity is just the number of molecules that react each step. So in step 1, we have two molecules, H2 and ICl. So that would be a bimolecular step. In the second step, we also have two molecules that are reacting. It's HI plus ICl. So that's also a bimolecular step. So now we have two steps, both of which are bimolecular. So that satisfies our second requirement of a reasonable mechanism. Let's go to the third one, which is usually the hardest one, and that is to get a theoretical rate law and then show that that theoretical rate law matches the experimental rate law. So remember how we derive theoretical rate law. It is going to be this rate law of the slowest step, okay? Since our slowest step is step 1, all we need to do is write a rate law based on step 1. And that would just be rate equals to K. The K for step 1 is just going to be called K1. It's the rate constant for step 1. And it will be the concentration of the reactants that are in step 1. And we have two of them. We have H2 and we have ICl. Now, both of them are going to be raised to the first power because the coefficient of this step is both 1 for the reactant. We can set order equal to stoichiometric coefficient because this is an elementary step. So this equation right here that I wrote is my theoretical rate law. And my experimental rate law is shown on the left. I'm going to just highlight it in yellow. It's rate equals K observed times H2 to the first power, ICl to the first power. That's exactly the same form as the theoretical rate law that I just derived here. Since the two of them have the same form, we can say that the third requirement also has been satisfied. So therefore, that mechanism that we're given is reasonable for the overall reaction on the top. Okay. I want to point out that that mechanism that we just talked about, I said that it was a proposed mechanism. Somebody actually had gone ahead and experimentally verified that the mechanism exists. In order for them to do that, they have to show that the proposed intermediate species actually exists. And in fact, you can do certain types of spectroscopy experiments to trap those intermediates and show that they actually exist during the reaction. So when you are able to do that, then you're able to actually construct an energy diagram for that entire reaction. So this is the actual energy diagram for that reaction. You notice that the reactant is right here, the products is right here, and there is two transition states here. We have one transition state here, we have another one here, but then there's this step right here where it forms a product in the middle, and that is the first step. So this part of the reaction energy diagram, that's step one of your mechanism. And then this one right here, I'm going to use a different color from here to here, that's step two of the mechanism. Now, just by looking at that, you can tell that step one is the slow step. And the reason is because the activation energy, which is the difference between the reactant to the transition state for step one, is much higher than the activation energy for the second step, which is just this one right here, okay? And so that tells me that that step is the slow step, first step right there, okay? That shows you how complex that reaction mechanism could be just for a two-step reaction mechanism. Okay, now we're going to go to the second type of mechanism that you often see for chemical reaction. And this is a mechanism where you have the first step being a fast step, and then the following step, either a second or a third, being the slower step. Okay, this is going to be represented by this reaction right here. This is the overall reaction. 2NO plus O2 goes to 2NO2. And we have collected a rate law from experiment, which is rate equals K observed times NO squared and O2 to the first power. So we're given this particular reaction mechanism, and we were told to check whether the mechanism is reasonable or not. So same idea like the previous problem, we're going to first see if the two mechanisms add up to the overall mechanism or not. This was already done for us, and we can see that that is the same as this reaction right here. So that requirement is satisfied. The next one is to test the molecularity of that reaction, and so we can see that this is a bimolecular because there's two NO that reacts with each other. And then the second step is also bimolecular because we have two molecules reacting with each other. So both are reasonable steps. Now the third requirement, and this is the requirement that you have to derive a theoretical rate law and show that that theoretical rate law matches the experimental rate law that were given. So remember, the theoretical rate law is the same as the rate law of the slow step. So our slow step is step two, so we're going to write a theoretical rate law based on that step. And that's just going to be rate equals to K2, since it's the second step, okay, time the species that are in the second step, the reactant, N2O2 raised to the first power, because that's the coefficient, and then O2 also raised to the first power. And I also wrote it in the notes. There is a problem with this rate law because you just look at this theoretical rate law equation and you compare it to the experimental rate law. Well, they don't look the same. There is rate, there is K, there's a constant, but then in the experimental we have NO squared, but in the theoretical we have N2O2. We still have oxygen in both, but there's clearly a difference in the two equations. So at first glance, it looks like the mechanism is wrong. But let's analyze it further. The reason is because this N2O2 is an intermediate. It's a species that's produced in one step and it's consumed in the second step. So it doesn't show up in the overall reaction. It's not present at the beginning or at the end. So you don't want to write a rate law using something that actually is not in the entire equation. You want to write a rate law that actually is represented by species that exist in the overall equation, whether it's the reactants or products or catalysts. Okay? So as a result, what we need to think about a little bit is how do we rewrite this theoretical rate law so that now it will contain species that are either reactants, products, or catalysts. And the way we do that is we need to look at that N2O2 concentration, which is the intermediate. So step one is this one right here. Let's think about how that relates to the other step. It says 2NO, and it has this funny symbol, and we'll explain what that is in a sec. N2O2, and it says K1 and K minus 1. Okay, so first off, that double arrow is what we refer to as a reversible reaction. So what that means is that they can go forward and they can go reverse. And when the reaction says that this is fast, it really means that this reaction has been completed while the second reaction is still going on. So that means that this reaction has reached a state that we call equilibrium. What does it mean to reach equilibrium? Equilibrium is the state where a reversible reaction is done or finished. If you think about a reversible reaction, it's a reaction where reactant goes to product, but then the product can go back and form reactant. So then the question becomes, when is this reaction ever finished, right? Because if the reactant goes to product, but the product can go back to reactant, that means that the reactant is never used up. Wouldn't that mean the reaction is never finished? So even reversible reactions can finish because we reach a point where the rate of the forward reaction is equal to the rate of the reverse reaction. And this, in fact, is what we call the equilibrium position. When the two rates are equal to each other, that means you don't make more reactant, you don't make more product. If you wait over time, the concentration of reactants and product is not going to change. So if you plot time here and then concentration of reactant and concentration of product, so I'm going to show this as blue here. So the reactant concentration initially started at a big number and then it drops down and eventually it just stays the same. The product concentration initially starts at 0 and then it increases until it stops changing. So the point of equilibrium is reached when these two concentration no longer changes over time. From this point on, all the way that way, then your reaction hasn't really changed. If your reaction doesn't really change as a function of time, that means the reaction is done. So that's how we determine whether a reversible reaction is complete or not. Now, how does that information help us though in order to rewrite our rate law? Because remember, our whole goal here is that we want to change our theoretical rate law, which is rate equals to K2 times N2O2 times O2. We want to express this a different way. Remember that we don't want this intermediate concentration to appear in our rate law. And we just said that equilibrium means the rate of the forward reaction is equal to the rate of reverse reaction. Since reaction 1 is at equilibrium, we can apply that concept here. The rate of the forward reaction is just K1 times NO concentration squared. Now again, how can I use the coefficient as my order? Because this is an elementary step. What about the rate of the reverse reaction? It will just be K minus 1, so that's the symbol for the reverse rate constant, times N2O2 to the first power, because that's the coefficient of N2O2. Now, how is this useful? Well, we know that at equilibrium, forward and the reverse rate is equal, which means that K1 times NO squared is equal to K minus 1 times N2O2. Our goal is to express this rate law that we derived earlier, this theoretical rate law, and get rid of that N2O2. So now we have a way to do that. We can use substitution to do that. So what we do is we just express this N2O2 as a combination of all the other terms, right? So it's K1 over K minus 1 times NO squared. I combine the K1 and the K negative 1 together because those are both rate constant terms. So now I have N2O2 being equal to this thing. I can take this, substitute it back into my theoretical rate law expression. So when I do that, this is what I get. Rate equals to 2 times, instead of N2O2, I'm going to write the stuff that I just find. K1 over K minus 1 times NO squared. So that's my N2O2 concentration, and then times O2. Okay, how does this help us? What we want to do now is check if this expression better matches the experimental rate law. Before I do that, I want to first look at all these constant terms. I'm going to just combine them together, and I'm going to call them just K. The K is overall the combination of different rate constants, but it's still a constant, times NO squared times O2. So this is now my theoretical rate law, okay? Now let's take a look at the experimental rate. Well, the experimental rate law is given to us here in red, right? It's rate equals K observed times NO squared times O2. But look, now they have exactly the same form as the theoretical law. The theoretical law is shown on the right at the bottom. The experimental law is shown on the left with red circle around it. And so we can see that they're the same form. They both have a constant term. They both have NO squared, and they both have O2. So therefore, that mechanism that we're given must be a reasonable mechanism because it satisfies all the three requirements that we had mentioned